Hello students, welcome to the classroom point. In today's session, we are going to discuss the concept of ethers. Let us see what does it mean by the ether. These are the organic compounds having carbon-oxygen-carbon linkage. So if any organic compound having this type of the link as the main principal functional group, such compounds are termed as ethers. So these ethers can be classified into two categories. They are simple ethers, which are also called as the symmetrical ethers, and next one is unsymmetrical ethers. Sometimes these are also called as the complex ethers. So in this case, simple ethers means whatever the oxygen atom is present in this earlier said functional part. So in these ethers, oxygen is attached with the similar type of the groups, same groups on both sides. See here, we have taken one oxygen and on other side, left side methyl group and right side also methyl group is present. And the name of this molecule is dimethyl ether or methoxymethane is the UPSC name. And in this case, oxygen is attached with the ethyl group and ethyl group. If the same alkyl groups are attached on the both sides of the oxygen atom, such type of the ethers are called as the simple ethers or symmetrical ethers. Whereas if oxygen is attached with the two different alkyl groups, then such type of the ethers are called as the unsymmetrical ethers. You see here, oxygen is attached to one side with the ethyl group, the other side with the methyl group, hence it is called as the unsymmetrical ether. Now let us see how to prepare the ethers. There are some important methods. In that first one is the dehydration of alcohols. And we have already prepared one video on the dehydration of the alcohols at different temperatures, because dehydration of the alcohols depends on the temperature. When temperature varies, the product also varies. So when you take the alcohols, generally primary and secondary alcohols at 140 degrees centigrade, actually we take it as a primary alcohol. So primary alcohols at 140 degrees centigrade undergo dehydration in the presence of the concentrated sulfuric acid to form ethers. Then what about the secondary and tertiary alcohols? When the same secondary and tertiary alcohols undergo dehydration in the presence of the concentrated sulfuric acid at the same temperature, they give alkene as the major product, not the ether. And if you take the primary alcohols, major product is ether, and this particular mechanism follows SN2 mechanism. We shall take some examples over here. You take ethyl alcohol here. So ethyl alcohol is a primary alcohol which on treatment with the concentrated sulfuric acid at 140 degrees centigrade produced diethyl ether. But if you take the isopropyl alcohol or tertiary butyl alcohol, this is secondary alcohol and this is the tertiary alcohol. So I'll mention it here. This is the primary alcohol, secondary alcohol and tertiary alcohol. So when both the secondary and tertiary alcohol separately dehydrated in the presence of the concentrated sulfuric acid at 140 degrees centigrade each, they produced alkene as the major product and ethers are the minor products, and this we should not consider. Major compounds are alkenes only. So that is the reason why in the dehydration of the alcohols using the concentrated sulfuric acid at 140 degrees centigrade to produce the ethers, preferably possible only with the primary alcohols, not the secondary and tertiary alcohols. So that is the reason why. Thus, in the formation of ethers, the dehydration of alcohols is in the order of primary alcohol, secondary alcohol, and tertiary alcohol. Let us see one of the important reaction in the ether, that is Williamson synthesis. Still, this reaction is considered as the most effective reaction for the formation of the ethers. Let us see what is the Williamson's ether synthesis. Let us take any alcohol. Alcohol when subjected with the sodium hydroxide or sodium hydride. You see here, alcohol on reaction with the sodium metal or sodium hydride, it produced sodium alkoxide. So thus sodium alkoxides reacts with the alkyl halides to form the ethers, not the aryl halides or vinyl halides. We shall discuss why aryl halides and vinyl halides are not to be considered or not to be taken. And this reaction also follows the SN2 mechanism. Most of the ethers reactions, either preparation reactions or chemical properties, they follow the SN2 mechanism. So here this alkoxide ion acts as a nucleophile. It attacks over the carbon part like this. You see, imagine this is the carbon, this is the bromine. So bromine being electronegative, then the carbon gets the partial negative charge. Carbon part gets the partial positive charge. So here this negative charged oxygen part attacks over the partially positive charged alkyl part of the alkyl halide and replaces the bromine in the form of the Br minus and bromide ion. So means one nucleophile replaces the another nucleophile. Hence it is called the nucleophilic substitution reaction. And this step takes place in a single step. Hence it is called the SN2 mechanism. And usually there is a question, there is a limitation in the Williamsons ether synthesis also. Which alcohols are to be considered in the preparation of the alkoxide ion and which alkyl halides are to be considered? Let us see them also here. If you want to take alcohol, so alkyl group in alkoxide may be primary, secondary and tertiary. So alkoxide means alcohol, you can take any of these groups, either primary alkyl group or secondary alkyl group or tertiary alkyl group, such as we shall take here. You can take the methyl alcohol as the primary alcohol or ethyl alcohol as the primary alcohol. Similarly, you can take the isopropyl alcohol secondary alcohol, or else you can consider the tertiary alcohol also. So the alkyl group in the case of the alcohols, this is the alcohol, these are all alcohols. So in alcohols, the alkyl groups may be primary or secondary or tertiary. But the problem arises only in the case of the alkyl halides. In the case of the alkyl halides, if you want to get the ethers, then the alkyl group must and should belongs to the primary or secondary, but not the tertiary. Why? Because if you take the tertiary alkyl halide, the tertiary alkyl halides on reaction with this type of the base, they don't give the ethers, but they give the alkene. Let's see some reactions here so that you may get the idea how to get the products. See here I have taken the primary alcohol. This is methyl alcohol and this is a primary alkyl halide, no problem. So that this alcohol actually do not directly react with the alkyl halide. Initially this alcohol reacts with the sodium, so that it forms the sodium alkoxide. So that here negative charge comes, here positive charge comes if it is the sodium. Then this negative charge attacks over the halogen bearing carbon, that gets the partial positive charge and the halogen gets the partial negative charge and replaces the bromide ion. So that bromide ion combines with the sodium and giving the sodium bromide, and finally we get the ether. But in this particular case, this is the primary alcohol, this is the secondary alkyl halide, even though the reaction gives the ether. But if you take the primary alcohol and an alkyl halide, the tertiary alkyl halide. Now let us see what is going to be happen here. Primary alcohol on reaction with the sodium, it forms its respective sodium alkoxide. Say it is sodium methoxide. Now this is the tertiary alkyl halide. Halogen gets the partial negative charge, as usually carbon gets the partial positive charge. Now this sodium alkoxide do not find a proper space to reach out to this partially positive charged carbon, as it is completely crowded with the methyl groups. And one side bromine is there, bromine is there, which is with the partial negative charge, and this partial negative charge nucleophile cannot approach from this direction as both are negative charged particles. So it has only one option to approach this carbon, exactly opposite direction to the position of this partially negative charged bromine. But at the same time, these crowded methyl groups, do not provide a proper space for this methoxide ion to reach out to this carbon atom, halogen bearing carbon atom. So that is the reason why this is being a base, not only nucleophile, alkoxides are also base. So initially, instead of attacking over the partially positive charged carbon, it will find another proper mechanism. That is, I'll write here, say this is CH2 and hydrogen. As I said earlier, this is the tertiary alkyl halide. Now, this partially positive charged carbon withdraw the electrons from all these carbon atoms, and these carbon atoms get the little partial positive charge being an inductive effect, and so that it withdraw the electrons from each of these carbons, withdraw the electrons from their respective hydrogens. So carbon hydrogen bond becomes very weak in all these cases. So this methoxide ion now can easily find the place to attack over the hydrogen to abstract. So what happens? This sigma bond electrons will shift over here, and these sigma bond electrons will completely shift over to the bromine, and finally providing the alkene. And since it is abstracting the proton, again alcohol will be reproduced. So this is the reason why we should not take the tertiary alkyl halides if you want to prepare the ethers, but you can prepare the ethers that are having the tertiary carbon group with opposite direction. Means, so here you take the alkyl halide as the primary alkyl halide, and alcohol must be the tertiary group. So tertiary carbon group, if it is having the alcohol part, now it forms the sodium alkoxide like this. Say, I'll remove this one. Just for example purpose I am writing after reaction with this sodium. So partial this is a negative charge, this is a positive charge. Now this negative charge can easily attack over the carbon and replaces this bromine, because it is a primary alkyl halide, this is a tertiary alcohol, and we get the mixed ethers, unsymmetrical ethers that are having the tertiary alkyl group. But the same compound cannot be prepared if alkyl part, tertiary alkyl part is the part of alkyl halide. So tertiary alkyl part must not be the part of the alkyl halide, it must be the part of the alcohol. Then only we get this type of the ethers. Then one more question. I just now said that we should not consider the alcohols, means vinyl. I'll show you here one important thing, that is CH2 double bond CH, bromine or chlorine or whatever it may be, with some sodium alkoxide or sodium methoxide, and this reaction is not possible. If you want to prepare this type of the ethers, CH2 double bond CHOCH3, and this type of the ethers cannot be prepared if double bond is directly attached to the oxygen atom. The reason here is, here in this particular case, lone pair of electrons that are present on the halogen participate in the resonance with the double bond, so that they provide this CH2 minus CH double bond Br plus. Now in this case, this alkoxide ion cannot break the double bond between the carbon and halogen. It is possible to break only single bond. So that's why we cannot prepare this type of the ethers. So ethers having the unsaturated carbon directly cannot be prepared using this Williamson synthesis. And you may ask the question, sir, what about can we take like this? Alcohol plus CH3Br. This is also not possible. Why? Because here OH group is bonded to the sp2 hybridized carbon. So when this type of the combination is there, immediately to participate in the tautomerism. So finally it gives CH3 CHO aldehyde. So there will be no alcohol. So that is the reason why this type of the combination is not possible. Let us see another combination. That is, what about can we take this type of the chlorobenzene with methyl alcohol in the presence of the sodium? Here you can't get the ether, but you will get the ether if the alcohol is the part of the aromatic ring. We shall discuss that reason also, the reason for this combination also, sodium. So here you will get the sodium alkoxide after reaction with the sodium. Here negative charge, here positive charge. It can easily attack over here, and bromine will be replaced, so that you will get the methoxy benzene, that is anisole. Then why this is not possible in this case? Why it is possible in this case? The reason for the not possible in this case is, I explained here. Chlorine here having the lone pair of electrons. These lone pair of electrons are participating in the resonance with the pi bond electrons of the benzene, and finally gives the double bond nature between the carbon and chlorine, so that this alkoxide ion cannot break this bond. So halogen, whatever alkyl halide we are taking, so alkyl halide in the case of the aromatic ethers must be from the normal aliphatic alkyl group, but not be from the aromatic alkyl halide. So aromatic halogens on reaction with the alcohols do not produce the ethers, but aromatic alcohols with the aliphatic alkyl halides produces the ether. And this is the reason why both of these compounds do not react with this silver nitrate. We know that silver nitrate has a more affinity. Silver ion has the more affinity towards the halogen atom. So immediately when it reacts with the halogens, if chlorine is there, means it forms the silver chloride. If it is the bromine, means silver bromide. If it is iodine, means silver iodide will be formed immediately if any halogen atom is present in any given organic compound. But these vinyl halides and halobenzenes do not produce the precipitate. The reason is, here halogen carbon bonds are not the single bond, they are the double bond in their resonance structures, so that the silver cannot react with the halogens and to replace them. Now come to the R regular point. So this is the reason why tertiary alkyl halides do not give the ethers, and similarly aromatic halides and vinyl halides also. Now let's see some application reactions here. See, here we have taken the one alcohol, which is a secondary alcohol and not the aromatic. No double bond is present. This is the primary alkyl halide, so that no problem. Just remove this HCl, means actually NaCl, so that we get the ether. And in this case, see, this OH part is from the aromatic ring is present here, and OH part is present, so that the reaction is possible, because whatever the phenoxide, paranitrophenoxide is formed here, it can easily replace the bromine and giving this molecule. But if you take the chlorobenzene and methyl alcohol, reaction is not possible. The reason is, here the lone pair of electrons participate in the resonance with the double bonded carbon atom, and which finally gives the double bond nature between the carbon atoms, so that reaction is not possible. But if you put this OH group here and chlorine group here, so that reaction is again possible. Why? Because here no resonance, here also no resonance. And there are some practice questions. We just practice these questions. I'll show you here, and the answers for these practice questions will be displayed at the end of the video. This is a practice problems part 2. So you pause the video and note down these questions and try to solve on your own, and finally find out the solutions for these questions at the end of this video. Now, another method for the preparation of the ethers is heating alkyl halide with a dry silver oxide. Just take the silver oxide Ag2O on reaction with the alkyl halide. Here you can take the same alkyl halides or mixed alkyl halides, but you will get the mixed ethers. If you take the same alkyl halide, same ether will be produced. And action of diazomethane in alcohol. And this particular method is only helpful in the preparation of the methoxy ethers. Methoxy ethers can be prepared using this method. Why? Because when diazomethane is reacted with the alcohol in the presence of the Lewis acid like boron trifluoride or hydrogen tetrafluoroborate, here the CH2 part shall be inserted between this oxygen and hydrogen. And already hydrogen is there. This hydrogen will be transferred to the CH2 part, which becomes finally CH3. So you will get the ROCH3. or OCH. This is called the methyl ethers. Okay, so whatever the compound, whatever the alcohol you take, irrespective of the type of the alcohol you take, you will get only methoxy ethers or methyl ethers. See here I have taken the ethyl group. Now you put the CH2 group between the oxygen and hydrogen. So you'll get the methoxy ethane. And you take the isopropyl alcohol, again you put this CH2 group between the hydrogen and oxygen and you will get this compound. And next one is reaction of lower halogenated ethers with Grignard reagent. So here in this particular case, we take the lower halogenated ethers and you will get the idea in next video where we are going to discuss the chemical properties of the ethers. So you will come to know how to prepare these lower halogenated ethers. These lower halogenated ethers on reaction with the Grignard reagent produce the higher halogenated ethers. 1 minute. This is higher ethers. So here Grignard reagent carbon part shall attack over the halogen bearing carbon atom and replaces the halogen. So that R part shall be connected to this halogen bearing carbon atom and giving the higher alkyl ethers. And the same thing here also you can see in this particular molecule. Methyl group will attack over this carbon atom and removes this chlorine, and finally we get this particular molecule methoxyethane. And the next one is alkoxymercuration or demercuration, followed by demercuration. Demercuration means removal of the mercury part. This is always possible only with the NaBH4, that you should remember every time. Alkoxymercuration, demercuration, wherever you do it, it is possible only in the case of the demercuration is possible only in the case of NaBH4. So in this alkoxymercuration and demercuration, generally alkenes on reaction with the alcohol in the presence of the mercury tetrafluoroacetate, it gives an intermediate compound that on react with the NaBH4 in the presence of the alkali part gives the ether. If you observe one small thing, that it looks like that Markovnikov's rule, but it is not a Markovnikov's rule, but it is similar to the Markovnikov addition. That's why I have written here. It follows according to the Markovnikov's addition, that is indirect method, because Markovnikov's rule involves the formation of the carbocation. But here no carbocation is formed. That's why we cannot say exactly this is Markovnikov's addition. But the products looks like the Markovnikov's addition. Means you take any alkene part. So in this particular alkene part, hydrogen of the alcohol shall be connected to the one of the double bonded carbon atom, and remaining alkoxy part shall be connected to the another double bonded carbon atom. And whenever a molecule is added, we have to disconnect one particular bond between the two carbon atoms. It is usually pi bond, which is a weak bond. So if you take the propene, hydrogen shall be connected to the carbon with more number of hydrogens. That means double bonded carbon with more number of hydrogens, and oxygen to the double bonded carbon with less number of hydrogens, and we get the this type of the mixed ethers. And this is a good method for the preparation of the mixed ethers also, and according to the Markovnikov's addition indirectly. Now let us see the addition of alcohols to alkenes. This is also one of the important method. Alkenes on direct addition with the alcohol in the presence of the acid catalyst to give ethers. You must remember that whenever there is an alkene and whenever there is an acid catalyst, there must be a formation of the carbocation. Carbocation shall be formed because of the positive electromeric effect. Okay, so that's why carbocation is the intermediate. Whenever carbocation is formed, you have to expect the rearranged products. You have to see for the rearranged product, is there any possibility for the rearranged product or not. So here let us take the this ethene molecule and alcohol in the presence of the acid catalyst. You take the hydrogen, add one side of the double bonded carbon atom, and remaining alkoxy group to the other side. And here also now this is an unsymmetrical alkene, this is unsymmetrical alcohol. So when alkenes are subject with the alcohols in the presence of the acid catalyst, obviously we get the ethers. So hydrogen shall be connected to the double bonded carbon with more number of hydrogens according to the Markovnikov's rule, and negative part to the double bonded carbon with the less number of hydrogens, C, and you break the one bond so that you will get the ethers. And in this particular case, the last one maybe just to see when this particular alkene molecule is subjected with the alcohol in the presence of the H2SO4, this was expected product, thinking that hydrogen shall be added over here and oxygen shall be added over here. But this is an unexpected and rearranged product that I said. So I'll show you how the rearranged product is going to be formed. This alkene molecule on reaction with the H plus N from the H2SO4. So positive electromeric effect, H plus N comes, so electrons will be shifted over to the carbon atom on which this H plus N will attack. So positive charge shall be created over this carbon, which gives the secondary carbocation. So this secondary carbocation is bit unstable when compared to the tertiary carbocation, so that's why this hydrogen shall be shifted over here. So hydride shift. So we get the CH3, CH2 and CH3. Tertiary carbocation is formed. And later we get the ethyl alcohol. The lone pair of electrons of the oxygen of the ethyl alcohol attacks over this particular carbocation so that they give the CH2, CH3, O, C2H5 and hydrogen positive charge, and this hydrogen will be removed so that finally we get the R rearranged product, C2H5, CH2 and CH3. So these may not be, I am writing just a small letters as may not be visible, just try to find out, and this product shall not be formed, only this product will be formed. And here whatever the H plus ion finally is released, not from the H2SO4, it is from the alcohol hydrogen. So if you take the deuterium over here, and finally whatever the H2O molecule is coming, that will have the deuterium. Or else if you take the D2SO4, then here you will get the D2, CH2D. So that you should understand. I'll take one example so that it will be very your doubt shall be clarified. Say I will take this particular propane molecule with C2H5OH ethyl alcohol in the presence of the deuterated sulfuric acid. Then the product is actually initially H plus ion from the acid attacks over the carbocation to generate the carbocation. H plus ion attacks over the alkene and to provide the carbocation. So that's why here what happens, CH3, CH plus, CH2D, because here D plus ion attacks, and this one will be attacked by CH2, C2H5 or positive charge, no, sorry, negative charge, lone pair of electrons. So the lone pair of electrons attacks from the alcohol part and finally gives the CH3, CHO, C2H5, hydrogen plus CH2D. This one loss of the H plus ion. So that here we get the CH3, CHO, C2H5, CH2 and D. So you must remember this type of the protonation, deprotonation, and where the H plus ion is going to be attacked. Why? Because whenever carbocations are going to be formed, this type of the reactions are so important. So I request you to subscribe my channel if you understand, and I'll show you the solutions for these questions. So practice questions part 1. Answers are this one. You please check with your answers. And practice questions part 2. Answers are these. And I hope you understand my explanation. Please do not forget to subscribe Classroom Point channel. Thank you.